Okay, this is the module on, or the introduction to 2D or double integration in polar coordinates. So far we've just looked at everything in Cartesian coordinates. But in previous courses, in previous years, you have been introduced to polar coordinates before. They're effectively cylindrical coordinates, I mean, without the z, and it's an easy transition from one to the other. But when we're in the plane, which we're right now, we're integrating things above a plane, but our surface is in the plane, the area over which we're going to walk, and there's a function over that we're integrating. Now we're going to talk about mapping ourselves out in r and theta instead of x and y. Now the relationship between Cartesian coordinates and polar coordinates you know already. So if you pick a point in space and give it xy coordinates, x is the horizontal component, y is the vertical component. Now we think of it as an angle and an extent. And we learned this way back when we first learned about 2D vectors, right? We don't think of it in polar as being in polar coordinates sometimes, but it certainly is. So we have some distance r and some angle theta, and x equals r cos theta, just trigonometrically. This is r cos theta, this is r sine theta. Okay? So to go from r and theta to x and y, we do that. And there are times we have to do that. To do the opposite, to go from x and y to r and theta, we say, well, r equals the square root of x squared plus y squared. That's the square root. Often we're just stuck and we leave r squared equals x squared plus y squared. You'll see that in lots of forms, but it's the same idea. There are times where r can be negative. It's not that r cannot be negative, it can be the minus the square root, and there are times where we have a certain angle and then we want to think of r as in the opposite direction. So r being negative just means go to that angle, and then instead of pointing r along that, you point in the opposite direction. It's a bit semantic, it comes up sometimes when we're mapping things out. We normally think of it as being positive, but we don't have to limit it as such. The sign rules of sines and cosines carry us through here, as do for this. The angle is the inverse tangent of the ratio of y to x, right? Which is because tan theta is y over x, so theta is the inverse tangent of opposite over adjacent, right? Okay, all stuff we know, we've known for a long time. What we're going to do now is convert our integral, which in general we think of as a semantic volume. I say semantic because it's like a mathematical volume. I mean, if F is the electric field and this is area, we don't think of that as units of volume, like in physical, fill it with water kind of volume. But mathematically, we think of this as a volume underneath this surface, right? So we kind of tend to use the word volume. So this is very general. Volume is an integral over a region of some function over that region times the area elements of that region. And this has no indication of coordinate system. For us, we right away convert it to x and y. And in those cases, dA was just a little box, so it was a little dx and a little dy. Now, we're going to write this in polar. And basically, you write your function in terms of r and theta, and if it was given to you in x and y, you would convert it to r and theta by replacing all the x's with this and all the y's with this. You have some crazy function of r and theta. That would be the integrand, the thing we're integrating. Right? The region we're integrating over, we have to define also in terms of r and theta. That's a separate thing. The big difference, the major difference between doing these multiple dimension integrations in other coordinate systems is the area element and later the volume element become not just like dr d theta, like they were at dx dy. They're now going to have r's and thetas in them, or other complicated functions of that. When we get to spherical, it's quite a mess. Not so much for dv, but other things we'll see. So the big-ish difference is that the area element is not dr d theta, it's r dr d theta. And what this is communicating or representing is the realization, okay, that if you've got a volume element, okay, the same dr, right, that's meant to be the same extent along the radial vector, and the same d theta, right? Because d theta is an angle, it's not an arc length. So d theta these are all at d theta. This area element is bigger than this area element. So this idea that dA is proportional to r carries the fact, or communicates the fact, or implements the fact that this dA gets bigger the further it is away from the origin, even at the same dr and the same d theta. Okay? That's what we're communicating there. Other than that, the calculus goes the same. Okay, okay. That's the new thing. It is true that it's not the most important thing, and I'm definitely not going to be using type 1, type 2 language in the context of polar coordinates. But when we think about the region now, not the function, not the integrand, the function we're integrating, but the region over which we're integrating, yes, it's true there are kind of two situations. And we're not going to do this very often. You could have something, right? Okay, where here we have some function of theta. This here is a function of theta, g1 and g2, okay? This theta 1 and theta 2, this limit of integration is not a function of r, this is not a function of r, so these are constants. And so you'd have some integral, right, of sort of theta 1, theta 2, then you integrate r from g1 of theta, g2 of theta, then you'd have your integral, and then you'd have r, dr, d theta. And you would do this part first, and when you're done, you'd have a function of theta, then you integrate out theta. This will be more obvious when we do the first examples, right? On the converse, you could have something that looks like this. Okay? And so, yeah. If this is our r, this is sort of, what do they call this when they call it r equals a? This is r equals b, so a constant arc at r equals a, r equals b, so if that's our limit, it has constant limits in r, but now here we have h1 of r is the bottom limit on theta, and this is h2, which is a function of r, that's the other limit on theta, and our integral would become from a to b, you'd integrate theta first, integrand r d theta dr. Okay. This will be easier when we see a first example, right? But the point being, just like when we did double integrals in x and y, when we do double integrals in r and theta, we have to understand the region we're integrating over, the floor we're walking on. We have to understand the function that's above that floor, the volume between which we're going to calculate. But we have to decide which way to integrate, which one to integrate first. Sometimes it will not matter. Sometimes it matters greatly. In principle, it does not matter, but it makes it easier or harder in certain circumstances. We won't do as many different crazy kinds of integration in polar as we did with Cartesian, I would say. And it's usually, I would say, in Cartesian, in polar, a little more obvious, I think. I admit, so I've got a couple examples we're going to record now. And the example that I do first in the modules, and the one I did first in class, may not have been a great choice. It's actually one of the harder ones compared to some ones after that. So we'll get to some examples through this now, and that'll make this sort of clear.